Hello students, greeting of the day. In today's lecture, we are going to cover the theory related with work energy principle, which belongs to unit number 6 of engineering mechanics. So this will be important for our end sem examination. So if we go through the exam pattern, there will be 3 numericals on unit number 6. Out of that, one numerical must be there on work energy principle. So to solve that numerical, we should know the basic theory behind that work energy principle. So in today's lecture, we are going to cover these 3 points. In that way, very first we are going to see the definition of work done. Then we are going to list out the different types of forces which we are going to consider to calculate the work done in the given numericals. And the third, we are going to see the work done of each force. Means first we are going to cover definition, after that list of forces and work done of each force in detailed manner. So let's start with definition of work done of a force. So work done of a force is a very simple concept which we studied in our school days. So the definition of work done is, it's a scalar product. It is a scalar product of force and displacement. Means for the calculation of work done, two things are important. One is the force and second is the displacement. Means work done is depending on these two parameters only, and it's a scalar product. So to define work done or to find out the work done of any force which is going to displace, we must know the scalar product, right? So what is scalar product? A dot B is equal to AB cosine of theta, where theta is the angle between A and B. So let us understand this concept through simple example. So let us consider we have a block resting on horizontal platform, and to this block we applied a force of magnitude F at an angle theta. So because of the action of this external applied force, the block is going to displace in this x direction. The object is going to displace in x direction. Okay, so force is there and it is going to displace through the distance s, means displacement is also there. So according to the definition of work done, what is the definition? Definition is a scalar product of force and displacement. So here force we have, displacement we have, and also we have the angle between the displacement and force is theta. So what is the work done for this particular force? So work done of F we can define as dot product of force and displacement, means F dot S, and F dot S, the formula for that dot product, how we get the dot product F dot S? F into S into cosine of angle between these two. So this is what the work done of external constant force. So in this way we can define work done of any force if we know the displacement. Sometimes we apply the force on the object, but the object is not going to displace. Do remember, if there is no displacement because of the external force, in that case the work done is 0. Now we are going to list out the various forces for which we are going to calculate the work done. Means if we go through the previous year question paper, then we are going to come across the different type of forces for which work done is asked. So we list out that forces. So the very first force for which we are going to find out the work done is the external constant force. Second, we have the frictional force. We need to find out the work done of frictional force. Third is the spring force. We are going to find out the work done of spring force. And fourth one is the weight. So weight is also one of the force, that is force due to gravity of earth, which is always act in downward direction for finite area. So from exam point of view, we are going to, or we must know the work done of this 4 forces. So let's see the work done of each force, the concept to calculate the work done for each force in detailed manner. So we'll start with the work done of external constant force. We are going to find out the work done of external constant force. So for this, again we are going to take one example, the example which we previously seen, the same numerical we are going to take here. Suppose we have a block which is resting on horizontal floor, and to this block if we apply external constant force F at an angle theta, and because of this external force which is acting at theta, the object is going to displace S. S is the displacement. Then the external force work done we are going to calculate by using the definition dot product or the scalar product of force and displacement. So work done of F is what? F dot S, that is Fs cosine of theta, where theta is the angle between direction of force and displacement, means the angle between force and displacement. In this way we can calculate the work done of constant force which is acting on object. Do remember, the work done of external constant force is always positive because of the action of force. According to Newton's laws, if we apply a force, the rate of change of displacement takes place in the direction of displacement, in the direction of applied force. Means if we apply force along positive x-axis, the displacement occurs in positive direction. So that's why the work done of external constant force is always positive. Is this clear? Next, we will see some other cases for the external constant force in which we are going to change the direction of application of force. Means in previous numerical what we studied is we have a block and we apply force at an angle theta, and because of that displacement takes place, that displacement magnitude S, and for that the work done is what? F dot S, that is Fs cos theta. But what if we apply the external force to this object in the direction of displacement? Means see here, the force is acting horizontal, and because of that displacement is also taken place in horizontal direction. Here the angle between F and S becomes 0, and cosine of 0 gives us the maximum value of work done of this external constant force. So for this we are going to calculate the work done as F dot S is equal to Fs only, because angle between the displacement and force is 0, therefore cosine 0 becomes 1. So that's why work done is direct multiplication of force and displacement. Is this clear? Now the important concept we need to understand or need to remember is, if that value of theta is 0, then we get the maximum work done of external force. And if the external force is acting 90 degree to the displacement, this will not be the case, because it is not possible to displace the object by applying 90 degree force. So that's why if that angle is 90 degree, cosine 90 becomes 0, the work done of external force which is acting 90 degree to the displacement, we consider that work done as 0. Okay. Now the work done of second force, that is frictional force. So the definition of this frictional force or the concept of this frictional force we already studied in the unit number 2. Coulomb laws of dry friction gives us the frictional force. So let's find out the work done for this. So again we will take the example of the block. We have one block which is resting on the horizontal floor, and I want to move this block by applying external. Means when the friction force develops, frictional force is what? It's an internal resisting force. Means when the object is going to move, the internal resisting force develop at the tangential surface to stop that motion, to resist that motion. So if I apply external force to this object and I want to move this block, suppose the weight of this block is W. Yes, this is in contact with the surface. So according to Newton's third law, every action has equal and opposite reaction. So normal reaction acts in upward direction, that is tangential to the surface, normal to the surface, and if because of the action, so here why I have shown the friction force opposite. Suppose if I apply external force to this in this direction, so the object, so this is the direction of motion of object, so this is what the direction of motion of object. So if the object is going to displace towards positive x-axis, the friction force act opposite to that to stop that motion, and this frictional force here we have. So what is the magnitude of this frictional force? According to Coulomb's laws of friction, we get the definition as mu s or mu k. It depends upon the condition of block. If the object is at impending, but to find out the work done, many times we are going to use this k, because impending motion means there is no displacement, and if there is no displacement means what? If there is no displacement, work done is zero. So most of the time we take this friction formula as mu k into normal reaction, and this normal reaction value gives us by applying equilibrium condition. So normal reaction equal to W if the object kept on horizontal surface, and in this way we are going to calculate the work done if the object is going to displace by this amount s, then work done of this is what? Force into displacement. So here interesting thing to know about the work done of friction is the friction force always oppose the displacement. Means for every case the direction of this friction force, means most of the cases the direction of this friction force and direction of displacement is opposite, so that's why this work done is negative. So here also we can take this as mu k into W into S is the work done of friction force. So what we need to remember regarding this, so work done of friction force is always positive. Yes, there are some examples where that work done of friction is also positive, but that is beyond the scope of our syllabus. Okay, is this clear? Next, work done of friction, we'll see some in the previous, what we see is when the object is displaced on horizontal floor, the picture will be something different if the object is going to displace along the inclination. So if object is displaced along the inclination, again the friction force is going to develop over there. So what will be the work done for that we'll see. Suppose we have one block which is resting on inclined plane, and this block is having weight W, and this block is going to displace in downward direction. What about friction force? It is acting opposite to the displacement, acting tangent to the contact surface, so the friction force act opposite, so work done is negative. And how we calculate that work done? Fr into S. Or suppose we have another block, the weight of block is W, and this block is displaced in upward direction. In this case also, if the direction of displacement is upward, friction force act opposite. In both the cases the work done is negative because friction always act opposite to the displacement. Then how to find out the work done of friction force for this particular case? So for that, first of all we are going to find out the FBD. We are going to draw the FBD of this block. Weight is acting downward W, so we are going to, and we know that when the object is in contact, normal reaction act normal to the contact surface. So to get the value of this normal reaction, we are going to resolve this W along and perpendicular to the normal direction. So the magnitude of component is W sin theta, W cos theta. So here by applying equilibrium condition, we will get the value of normal reaction as W cos theta. So we'll find out the work done as mu k into normal reaction, where normal reaction is W cos theta. So work done of the friction force when the object is moving on inclined surface, then the work done is mu k into W cos theta into displacement S, and work done is always negative for friction force. Is this clear to you? Okay. Now we'll see the work done of next force, that is work done of spring force. So first of all we come to know that, or first of all we need to understand that is there any force in the spring. So we have the photograph here, I have taken it from the internet. So the first case represents it's a spring having undeformed length, means we haven't stretched that spring or compressed that spring. So this is the undeformed length, means original length of a spring. In case 1, if we stretch that spring by distance x, if we stretch that spring by displacement x, then definitely the spring force is going to develop inside the spring, and this spring force tries to bring this particular spring to its original position. Means if we displace the spring away, the spring force acts opposite to that. Means here we come to know that the direction of spring force is always opposite to the displacement of the spring. We can see the second case when we are going to compress the spring, means we are going to move the spring towards left, then spring force tries to bring this particular spring to its original position. So here again the direction of displacement and direction of force develop in the spring acting opposite. So that's why the force developed in the spring we are going to define as negative force, and the formula for that is minus k into x, where k is what? Spring constant, and x is the displacement. So if this is the force, then what will be the work done of it? So here we have the formula to calculate that work done of spring. The formula is half k x1 square minus x2 square, where k, as we discussed before, stiffness of spring or constant of spring, which we are going to measure in Newton per mm or kilonewton per meter, and x1 is the initial deflection of the spring in mm, x2 is the final deflection of the spring in mm. So it is very interesting to know when this work done of spring is positive and negative. So this formula we have half k x1 minus x2. So this work done of spring is positive or negative is only depends upon the values of x1 and x2, means initial deflection of the spring and final deflection of the spring. So what we are going to conclude from this particular formula, if the value of x1 is greater than x2, then work done is positive, whereas if x1 is less than x2, the work done of the spring is negative. Is this clear to all? Now the last is nothing but the work done of weight. We know that weight is nothing but the force due to the gravity of earth which is acting in downward direction for finite area. So let's understand the work done of this particular weight through some examples. So on left hand side we have one block. The weight of that particular block is W. We know that weight is acting upward, whereas if the block is displaced in downward direction, see here on left hand side we have the block W whose weight is acting downward, W, and the block is going to displace in upward direction, means displacement is upward. So direction of force is downward, direction of displacement is upward, means force and displacement acting opposite to each other, means work done will be definitely negative. So how we calculate the work done for this? So work done of the weight is nothing but W into S, as the angle between these two is 180 degree, cosine 180 means negative. Okay, so if the direction of force and displacement is same, work done is positive. If the displacement and force are acting in same direction, work done is positive. We'll see the second case. We have another block having weight W, and here the weight is acting in downward direction, means displacement is downward, means the direction of weight and direction of displacement is same. So the work done for this particular case of weight is multiplication of weight and S, and as both are acting in same direction, the work done of weight moving downward is positive. So these are the cases where the weight is acting in vertically, or weight is going to displace in vertical direction. So what if the weight is acting on the inclined surface? How we are going to find out the work done for it? So let's assume we have one block whose weight is W acting downward direction, and this block is moving along a inclined plane. So the block is going to displace along inclination at an angle theta with horizontal. So here we need to resolve this displacement of block in the direction of weight, because weight is acting vertically downward. So we need to resolve this displacement, inclined displacement, into two components. And for the calculation of weight, we are going to consider the displacement in the direction of weight. So here the block is moving in upward direction. Here the block is moving in upward direction. So the displacement upward, weight is acting downward. Both are opposite to each other, means work done is negative, and the magnitude of that work done is W into component of displacement in the direction of weight. So S cos theta into W, acting opposite, negative work done. So this is what the one case. In another case, if the block is moving in downward direction along inclination, we know that weight is acting downward direction, and the displacement in vertical direction is also downward. So the magnitude of work done will be W into S into cosine of theta, where theta is what the inclination, and both are acting in downward direction, so work done is positive. So in this way we are going to find out the work done of weight which is displaced in vertical direction or along the inclination. If the weight is displaced along horizontal direction, the work done will be 0, because we know that weight is acting downward, and if the displacement is horizontal, the angle between them becomes 90 degree and work done becomes 0. So these are the few cases which we need to consider, or we need to understand while solving the numericals on it. So that's it from this lecture. Thank you for listening.